I've had one of these kicking around in my junk box for quite a while. It's an XR-2206 Monolithic Function Generator. According to the blurb, it's capable of producing high-quality sine, square, triangle, ramp and pulse waveforms of high stability and accuracy. The output waveforms can be both amplitude and frequency modulated by an external voltage. Frequency of operation can be selected externally over a range of 0.01 Hz to more than 1 MHz. Which sounds very good, although the 1 MHz claim has a few caveats which we'll come to later. Anyhow, I was trying to think of something useful I could do with it, and I thought about trying to build a signal generator around it. To get a feel for what it can do, I designed a minimal test circuit. In this configuration is set up to produce triangular waves. The frequency is determined by a capacitor connected between pins 5 and 6, and a resistor from pin 7 to the negative supply rail. According to the datasheet, the frequency should then be 1 over RC. So I wired the circuit up on a breadboard and set out to test that. With a 100k resistor and a 100 nanofarad capacitor, I got about 120 Hz. That's probably within component tolerances. I selected the resistors to be fairly close, but those are not high precision capacitors. Changing the capacitor to 10 nanofarads, I expected a frequency about 10 times higher, and I got about 1 kHz. 1 nanofarad gave me 11 kHz, but with 100 picofarads I only got about 84 kHz rather than the expected 100 kHz. Although looking at the datasheet a bit more closely, that combination is actually outside the recommended range of values, so I probably shouldn't have been surprised. Next I tried a 10k resistor. With the first 3 capacitors I got frequencies about 10 times higher than before. Including the 100 kHz that I failed to get earlier. But with 100 picofarads, instead of getting 1 MHz, I only got about 700 kHz. I seem to be running into some sort of limitation there. Also, the waveform was starting to look more like a sine wave than a triangular wave. I also tried a 1k resistor, and again I got the expected results up to about 100 kHz, after which it started to go a bit wonky. I tried some more capacitor values and managed to find ones that would give me 1 MHz and 2 MHz with the 10k resistor. But it seemed I'd have to pretty much abandon any hope of getting a good triangular wave at those frequencies. Here's a summary of the results. In the green area of the table things are working well, but in the yellow area the frequency departs from the calculated value, and the waveform starts to become rounded off. The output amplitude also becomes lower, but I'm not so worried about that. I can always compensate by adjusting the resistor connected to pin 3. So here's what I'm thinking at the moment. One pole of a 2-pole rotary switch selects the frequency range by switching in different timing capacitors. The other pole connects an appropriate resistor to pin 3 to keep the output amplitude constant. The timing resistor pin is connected to a 10k fixed resistor in series with a 100k variable resistor, which should allow the frequency to be adjusted over about a 10 to 1 range. The frequencies marked on the switch will be obtained when the frequency adjustment knob is all the way clockwise. It was getting a bit messy and unreliable doing all that on the breadboard, so I had a look in my junk box for a suitable rotary switch and attached some capacitors to it. Then I wired the whole thing up to the breadboard and tested it. While doing that, I discovered that the capacitor values I'd shown you here on this diagram were out by a factor of 10. This is what they actually needed to be. So I moved all the capacitors over and added a 1 microfarad for the 100 Hz range. Ideally it should be a non-polarized type because there's no DC bias between the timing capacitor pins of the chip. But I don't have a non-polarized 1 microfarad handy, so I'm just using electrolytic for now. I also tested the frequency adjustment and made sure it gave me the range I wanted. The next thing was to figure out what values to use for the amplitude resistors. I connected a variable resistor, and for each range I adjusted it until I got an amplitude of about 1 volt peak to peak. Then I measured the resistor value and wrote it down. That gave me this list of values. Clearly these are not standard values, so I'm going to need some combinations. To help with that, I wrote a Python program that calculates all the series and parallel combinations of two E12 series resistors. That gave me a list looking like this. From that I selected these resistor combinations. That led to this circuit, which I assembled on the other half of the rotary switch. This is just for testing, it won't be as messy as this in the final build. Yeah, I know, that's what they always say. Beautiful. Time for another test. I've put some markers at 1 volt peak to peak, and I'm looking for the amplitude to stay about the same as I change ranges. There was a bit of breadboard wonkiness here. It's okay again now. That all seems to be alright. As you can see there, I was having some problems with breadboard flakiness. So I decided to rebuild what I had so far on a piece of perf board. After doing that, it worked much more reliably. The next thing I like to do is arrange some kind of output level control. Here's the kind of thing I have in mind. A set of fixed levels to choose from plus a continuous adjustment. But that's something for another video, so I'll see you next time.